Hi everyone. So we're going to go back to trees and graphs right now, and this is the first of many, not many, but a fair number of lectures on for visualization for ITEC 2100. In case you're new to us or just some random person on the internet finding this lecture, we're going to be looking at trees and graphs, and we've already done a number of talked about what a tree actually is, what a graph actually is, and we've also looked at a number of examples. But I wanted to sort of finish this off. But before we go on, let's have a look at what the rest of term looks like. So I like to say in advance that these are going to be longish videos because I'm just going to be giving a lecture and recording it versus trying to polish it up and have special effects and that sort of thing. So the idea here is, and I know some of you may not do this, but the plan of attack is that while we do while I do these videos, you should take a pause, especially if there's something that's confusing. Take a pause, especially if there's little mini exercises in there. Try out the exercises, see what you think. Ask questions on Piazza. Contact me via for office hours, whatever the case is. Um, the videos will be crappy. Will be ums and ahs. There'll be me stammering over my words like that last sentence was. But this is the best we can do for this situation, just because of the time constraints and everything else like that. It's a rather large pivot for a class. This class is also is designed from the ground up to be supposed to be highly interactive throughout the term, and so therefore this is really suboptimal for this particular class. Um, to give you some milestones coming up, the user evaluations, or I should say usability testing. Let's say usability test. Let's change this up. Just so we don't forget. The usability testing is going to be coming up. We will continue to do it. Of course, we won't do that face to face. This was a surprise for last Thursday, Wednesday or Thursday when we were discovering, oh, all sports shut down. But for usability testing, what we're going to do is each group is going to post their visualization. Presumably, it's going to be on a URL, and each group would post the URL of their visualization. Every person from every single group will go and try and evaluate the other groups. That will be, doing a planned task for the other group, and then giving your feedback and your comments. So for your evaluations, you'll have a set of instructions to give people. People would read the instructions, try doing something. Let's say, so for the red light cameras, maybe you tell, so shredding reds, maybe you say, okay, go and look for red light cameras in your area of town, or maybe you say, go look for red light cameras in the glebe, or this particular red light camera in the glebe, whatever the case is, whatever the task is, and see how many accidents are surrounding that area. For the festivals, it might be go look for the cheese festival, or it could be look around in the summer months to see what festivals you want to go to. It's up to you. The more constrained the task is, the easier it is for you to plan for that particular task, but the less realistic it is for how people actually use your system. If you say, click these four things, and they click those four things, okay, that's not that useful because all is that they could follow instructions. The more open-ended it is, the stronger your results, or the stronger you can make claims about how useful the system is, or if people can actually use the system. But the more open-ended it is, the more things you need to be able to support. The other option is you can say, hey, try this out, play around with it any way you want, try these things out as suggestions, but this, and this are not implemented. So if you cannot zoom into the map, tell people you can't zoom into the map. That's okay. I realize that this is very difficult at this stage, especially without any kind of labs. It's going to be very difficult to get the ideal visualization that you were looking for. That's not the point of the course. Is not to make the perfect visualization that you then sell, for millions of dollars. It's for you to go through the process of learning how to make a visualization and actually doing at least a decent job given the circumstances. So, if you are worried about being able to do a particular plan, or if you can't figure out how to make zooming work, for example, just acknowledge the fact you can't do it, and we will work around it. Ask me questions as well about that, just in case there's anything else that comes up. But make sure that when your people are evaluating your system, they know not to try and zoom into things, or if it doesn't allow zooming, you tell them that it doesn't allow zooming so that they know in advance. Okay, so the final presentations themselves, originally they were meant to be face-to-face, group of people, much like we did with our final sketches presentation. It was meant to be a limited presentation for each group, and then you'd show a little video in the middle of it, and then finally we'd open the floor to questions. Since we can't do that, my plan of attack is this: each group would record a video fully explaining what you're doing for your project. It can be as the level of crappiness as this video, for example. So it doesn't have to be overly polished or anything like that, but it does need to get the point across, and we need to be able to understand what you're saying and be able to follow along what you're doing. So doing a presentation, but it can be like a live presentation of a PowerPoint slide or a PowerPoint slide presentation. You can still show your video that you wanted to make beforehand. That video should still be done, because that video is what you pass off to potential employers when they want to know what your system does or how well it works. You can then reuse this and pass this off when you're looking for co-ops. That's why we have that video. Not for me, it's for you. So at the end of so you give up your presentation, you can show your video during your presentation, like we're going to for some of these videos here. And then when you're done, then you'd pass, after all that's done, then you'd pass in a PDF of your report. Let me state, the PDF, the final report, should be fully self-contained. So I shouldn't have to look at the video, I shouldn't have to look at your previous sketches, I shouldn't have to do this or shouldn't have to do this. If you pass this report to any old person, they would know exactly what you did throughout the term. That doesn't mean replicating everything you did all term, but it's not relying on, oh yeah, I gave you those sketches before, right? If you gave me some sketches before, don't just refer to the sketches before, show me the sketches from before. I'm going to only have a PDF in front of me. I'm not going to be hunting down what you previously wrote in another report. Put it in there. If you're afraid I'm not going to see it, put it in the report. The reports can be longer than a set number of pages. I'm not going to penalize you for having it too long. It's going to be penalized if I can't follow along what you're trying to say. Finally, office hours for this course are going to be sporadic. I'm trying to do normal office hours, and maybe if everything will settle down once I've gotten a number of these videos, in the can for people to be able to use. I know 1400's videos are all done. I'm hoping I can get 2400 and this done within a week or so. And once I'm doing that, then I may be able to handle things. But I also have 2 little kids running around, so I will try and answer office hours questions both before, during the 9 to 5 time, and also afterwards as well, like at night. It might make it easier to do it that way. So if you have questions and you don't want, write an email if you need to. Face-to-face is also perfectly fine. I prefer face-to-face in many cases, but it doesn't have to be. Just ask questions. Don't just suffer in silence. Don't assume that you have to finish something. Ask a question. That's fine. That's what the point of office hours are. So please take advantage of that as much as you can. So last time around, I think I had another slide. Oh, it's in the wrong order. Last time around, we were looking at graphs. Before, we're going to go switch back to evaluations for a second, but just to remind you, we looked at networks or graphs, and we talked about, we had particular nodes, and we have edges. So we have a vertex or a node. Or a link, depending on what terminology you want to use. And we can implement it or represent this information in a variety of different ways. You guys gave me some great different ways of representing this same graph. I actually don't like this graph particularly compared to some of your answers that you gave me. We talked about the fact that we can represent quantitative, so continuous data with different colors, like a saturation level. We can represent categorical data with different shades or different hues. We can represent categorical data via the kind of hatchwork or the kind of pattern that the arrows actually have, or sorry, I'm dropping a pen here. The kind of shape that the actual vertex is, right? All of this can be used differently. You can use different levels of saturation per vertex to represent continuous data for the vertices, right? It's somewhat up to you. The Even the directionality of the edge, you could have something like that for the directionality of the edge. You could have it do that thing. I don't know. Almost anything goes. That's sort of the point. Just because you're just showing the relationship between different entities and what they're connected to, it doesn't have to just be a line in circles. And so you can encode multiple bits of information at once. We also looked at the fact that this is such a ubiquitous and common problem that they actually have algorithms for how to lay these things out, because they get so big and so convoluted. We need some nice ways of laying out a graph. Now, in some cases, it might be a mesh, like we're talking about for this particular graph viewer test application. But in many cases, it might be the network that is your either a social network or or a network of computers. And in both of those cases, I have certain rules that I want to follow. Those rules end up being those rules end up being things like trying to minimize edge crossings, trying to reduce the number of overlapping edges, overlapping entities, clustering, grouping together, things that you would expect to be straight lines. Like I have a continuous set of points, I expect them to be either in a straight line or in a curved line. Vertices are drawn by specific sizes. Things that are similar are grouped together. I can use nearby vertices should be grouped nearby each other, things like that. If I have a structure, for example, like down here, if I have a central point, I actually put it in the center of a wheel, essentially a hub spoke relationship, because that is the central point for a whole bunch of different vertices, and people naturally gravitate to this being laid out. I want to minimize edge crossing, so I actually like this over this. I want to lay it out in, so I want symmetry. I want to avoid outliers. I want to avoid crossing. There's a whole slew of different things, and if you want to look up any of these rules, feel free. Most of the time, I'm not going to be grilling you on this. Some of these rules I might, point out if you do them incorrectly, but for the most part, you're trying to make it sort of an idealized layout, and if you have any pre-made solutions, they work relatively well. Now, the job hunting group, your visualization is actually using what's a spring force layout algorithm, and it actually is showing all the gory details for all the various jobs versus just the current skill set that you're looking, or the current skill that you have, then the jobs related to that skill, and then the skill set related to the jobs that are related to the center one. So I was actually looking for a subset of the entire graph at any given time, and the layout is this sort of thing. It is what I'm currently looking at: job, job, job. So let's actually make the jobs a square. Right? It's a sort of a custom graph versus something that you would just get a pre-made graph for. So I have a custom skill, and then I have a bunch of the related skill sets that are associated with that. Right? It is very custom, and I'm not sure how hard that is, but that is a different way of doing a graph layout. It is following this central placement for the central idea. The placement actually tells you something, and then I have what's directly connected to that, and then the indirect connection, and I keep on changing shapes as I go out. Again, laying it out sort of in a fan formation. I'm not sure how hard or easy that would be for you guys to implement, but that's the sort of thing I had envisioned. So, but first, before we go into networks even more, I want to just do a quick this was our in-class task. I'm not expecting you to write the in-class task or put things on the Google Drive, but I just wanted to point out, and that sort of the font looked like crap. The fonts have changed when I did a copy and paste over to another thing I didn't notice. So if I'm doing this final evaluation, if I had an ideal final evaluation, what would you do? So I want you to think of two different things. First of all, I need you, each of you, or groups, to think long and hard about what's the task you're asking people to do. How do you know you're being successful with your visualization? So, are you expecting expert users? Are you expecting novices? Who are your end users? And what's the task you really want to know if it works or not? So, if it's finding a job, if it's a job finding task, then maybe it's you present them a whole lot of job options. Say you have this particular skill set. You can make it artificial. It doesn't have to be that person's skill set. You could say, okay, you're a lifeguard. You have CPR accreditations. You have CPR training. What jobs are available to you, and find the job that pays the most out of the jobs available to you. And then ask them another question like, and tell me what other jobs you need to acquire as a lifeguard to make sure that you get the maximum amount of money. Something like that. You can frame your task to be something artificial, but you still want them to do a task that you know is actually going to really test your system. If you're asking them, can you click on this button, you're wasting your time. And I'm not going to believe anything you say about your evaluation either, right? If you're talking about the Toronto safety group, our group work, right? And we say, show me if we're the whole point of that project was you're trying to look. You were originally supposed to be looking for a house in the Greater Toronto area, and you're also evaluating how safe a particular neighborhood is. If your evaluation was click on a neighborhood, that's it, then that's a useless evaluation. It's not really testing things. If you can say find a house in the Greater Toronto area that you find would be safe, that's a fairly accurate representation of what you're trying to do. Maybe it's how safe are houses in Roncesvalles compared to North York or some other place in Toronto, right? Or maybe it's is this house that you're a house in this region? You're thinking about buying a house in this region. How safe do you feel this house in this region is? Right? If you're talking about how the safety areas for Ottawa, for example, and people looking at white collar crime and accidents and that sort of thing, what do you want people to be able to take away from your system? It's not whether they can filter, it's what they can do with your system. And so your tasks should reflect that. But besides all of this, I also want you to think long and hard, maybe as a group or as an individual right now. You can pause the video in a second. Think about if you, in an ideal world, how would you actually evaluate your system? Not for this class, but when you finally polished it up, what would be the circumstances that you would like to use to evaluate whether this thing works? And keep in mind that just controlled studies in a lab are not always the best. Maybe you want to deploy it and see the real world examples. Maybe you want to release it to the real world, log the data, and then collect all that log data and analyze it. Maybe it's you observe people using your system. Maybe it's you can almost come up with any scenario in this case, right? How many times that you can infer whether red light traffic cameras actually cause accidents or not, or people can come to that conclusion, or do they come to that conclusion? What kind of conclusions do people come up with? That sort of thing. Like in an ideal world, how would you test your system? So I want you to pause the video for about 5 minutes. Come think about that, and then we'll pick up from there. Okay, for those of you that paused, I'm not expecting. Some of you probably did not. Some of you probably didn't even notice I was talking. There's no one right answer for this. What I would like you to do is think about what you ideally want, because once we know what the ideal is, we can roll back from the ideal to something satisfiable. We cannot, if you just randomly guess at what your evaluation is, it's going to be disappointing. So your evaluation should be accurately reflecting what people actually want to do. I'm trying to think of a good example for. I always go back to that application where it was punishing users. So that application, I don't know if you remember, it was the what did I call it? The Buckley's evaluation, or the Buckley's application. So they were going to essentially punish users, or just keep on pestering users if you were not reading, or if you're not doing this or you're not doing that. And everyone agreed, yeah, everyone would just uninstall from their phone. And then I said, well, the point of this application, you could get people on board if they bought in, just like I think there's some exercise or bad habit things where they put it's essentially blackmailing you. You put in a certain amount of money, and they keep that money if you break your promises about not smoking, for example. So there are existing applications that do this. The question is, how would I evaluate that sort of system? What I would not want to do is just see if people can click things. The whole point of that system is you need to figure out if people would be willing to use that system, or if they would just uninstall it. If you give them a very artificial scenario, in that situation, you're not actually accurately seeing if your system would be useful. Your job is not whether they can click certain things. Your job is to figure out if you are solving the actual problem, or at least attempting to solve the actual problem. So if it's festivals, you see if people can actually find a festival that would suit a certain set of criteria. If you were talking about dangerous intersections, can you identify the more dangerous intersections, or the intersection around your house? How dangerous is it compared to the rest of the city? Right? It's the task that people are actually going to try and do with your system. That's what you're aiming for. So, how many people would you need to have? If so, you check for your ideal. How many people would you love to be able to evaluate this with? Over how long? Do they need multiple exposures to your system? That sort of thing. What kind of statistical tests are you doing? What kind of data are you collecting? Are you collecting qualitative data like interviews, or are you collecting quantitative data? And these are the kinds of things that I want you to play with and mention them in the report. That's a great use of this, right? Ideally, we would test our system using X, Y, and Z. For this usability test, we tested this particular scenario because that was our priority. We wanted to make sure that the filtering button worked correctly, or whatever the case is. So let's go back onto the graphs. I love talking about the underground, and particularly the history of the London tubes. This is a great pause the video if you want. You can read this thing. I'll be rehashing a lot of large chunks of that video if you want. And I've already mentioned it a little bit in class, but I love talking about this. This visualization or this series of visualizations, they're well established, they're well studied approaches to visualizations. In fact, let's just pull it up anyways. Hopefully it'll just open up properly. All right, here is the original. Okay, you'll hear all sorts of, oh my lord, you can stop now. Here is a number of, there's a history of the Underground Railroad. Not that Underground Railroad, the London Tube system. Notice this would be one of the original versions of it, right? We have a nice green line. Nice, it does all this little turning around. Here's where London is. Here's a whole bunch of lines. As you might imagine, now in retrospect, you look at this and you go, well, that's not very useful, or that's problematic. Look at how this looks compared to what we just saw. Here is when they expanded it. I mean, look at this thing. Good luck being a tourist in London while looking at this thing. It's a good thing that you know where this farm field or whatever the hell that thing is, right? I need to know where that lake is up there, right? This is what the original London Underground maps were looking like when I zoomed out. And the big takeaway for many of these things, so this is the 1926 tube map, and this is what one of the workers someone was working in the underground, and as just an employee, not a map maker or anything like that, and he comes up with this. And the big takeaway is it's an underground railroad, as in, I don't need to know where that lake is. I need to know this river because this is the context. Remember, focus plus context. I need to know where the river is to give approximate ideas of, is it one side of the river or another? That is a major milestone for the city. I need to know where things are going. But what I don't want is weird random squiggly lines or anything like that. There's no need to actually show a curved line here. I want straight lines. I want text to be horizontally aligned. Look at this. I got this little text on the side here. Right. The more, if I'm putting in this much information, I need it to be horizontally aligned text, and I want to have some kind of iconography showing what these nodes are. And if I have special nodes, like if there's a connection, I can use a empty circle to show that there's a connection. I can transfer from one line to another. There's a very clear iconography. The lines themselves are a particular color, so you can actually figure categorical data. They're using hue. I'm using hue to tell me exactly where things are, what line I'm on, and I can figure out the red line versus this, right? I can figure out where things cross over, and I can figure out, and I can easily see where everything is in space. The takeaway though is I don't care if the line turns. I care where the next point is. It's a graph. It's not a map. That's what makes it special. That's the big takeaway. And when you see someone do this wrong, it's infuriating because it's a graph. I don't care where it is in space. I care what it connects to next. I care when I pop out from underground, but that doesn't have to be actually accurate. If I know I'm getting off at Downtown Crossing, or that's Boston, by the way, Lancaster Gate, or some other place, I sort of know where that place is. Even if I don't, I go from this map to another map and know where the subway is. What I don't want to do is try and force this into the general map of London. The map of London is way too convoluted. So here's an even this is the next version of it. Like, it keeps on getting better and better because you get add more and more lines. But you get rid of there's no the color background, get rid of it. It's yellow, it's harder to read. Make it white. Make it bolder difference between what you're reading, because we read based off of the differences in brightness. We're using a whole bunch of different colors to show the categories which stop, and the text itself is in a particular color, so you know it associates with that, right? Basic Gestalt principles. And then we get worse and worse. Look at this giant block. They've after the original designer died, or maybe I don't think he even died. They just started listening to him. They started making these giant connections. This is where the connection is, and it's way too. And then look at the river. It's jaggedy for no reason. It's just terrible. Oh, and then we get even worse, right? So after Beck, we get it to like this level. We get to this level. Ultimately, this is here. I think this is a final tube map right now, because we have different zones we need to encode. That's why we have the different grays and whites to encode different zones. Fairly subtle, but important, and we do need to encode that. We have almost perfect 90-degree angles everywhere here, because that's what people prefer to see when they're seeing this. And the actual dots themselves are fairly straightforward. They're perfectly horizontal. There's no way in heck you could have represented this level of complexity in the original map with all these twists and turns. It just wouldn't have worked as well. Like, the river itself is going at completely 90-degree angles here, right? It doesn't matter. It's meant to be, that's where the river is, that's where your line is, that's what I care about. Did I just go into another zone and have to pay more money? And so that's one of the big takeaways for the London tube map, is this idea that a tube map, or any kind of subway map, or metro map is actually the term for them. I really want to care about how to get from point A to point B. So I need to know what connections, I need to know where to get on, where to get off, and approximately where I'm going based off of some rough landmarks. But I do not need precision. And people can go crazy with London tube maps. I did not make epidemic rapid transit map. We're talking about how pathological things can go transfer around the world. I did not put this slide in with the coronavirus. This was from last year. But yeah, it's people have used it in all sorts of horrible ways, and I don't necessarily like this way, but it does sort of represent what we're talking about. There is even the cosmic web. It turns out that a lot of cosmic entities, because that's like celestials, or Thanos. So like the cosmic web is something like you can actually see connections, gravitational connections between different stars, different planetary bodies, different parts of the parts of the universe, and how they're actually interconnected. And there are essentially invisible threads that connect these various things, and showing the network how these things are actually interconnected. But then there's also this one, and I'm going to strongly recommend you watching this video by yourself. I could play the video, but you're watching a video, so that's not very useful. I strongly recommend it because this also directly relates to storytelling through visualization work, which is closer to what you guys are actually doing. This is less about inferring useful bits of information or data discovery on the part of researchers, and more along the lines of, can I convey to other people what's going on here, like how people are moving from one place to another. This is migration of people over time from major cities in the world. So London, this would be Paris, I do believe. Rome's down here, and all these various major cities around the world. And if there's a net loss or a net gain of people, so blue is gain, I do believe, or a net loss of people from that place to other parts of the world. If they're migrating to one place to another, and it's an animated transition of these points from one point to another. The network is on the map itself, and the arcs are the edges connecting these things. And the sheer number of lines is actually representing an edge and how much of a weight that edge has. It's just a cluster of lines instead of in a single line. We could also do things like this. So we can hybridize things. And this is, I think, a great little video. Again, I strongly recommend having a look at this video. It is fascinating what you can do with all of this. They show brushing and linking. They show how represent multiple different things. It's very dense in terms of what they're trying to say, but once you see the video, you're like, oh yeah, that's all they're doing. We can essentially, each of our nodes or each of our vertices can be a graph in itself. It can be a visualization of itself. So I can do small multiples, I can do a line graph, I can do a tree map, I can do whatever I want. And the connections between this node and that node, or this region and this region, can be represented by the edge, the thickness of the edge, and I can actually show how many from this green region are going to blue, how many from the blue are then going to this, that sort of thing. I can do the transfer from the green region to the red, and so I get this color transition from green to red between the two, and how many people are going from Arizona to Montana and from Montana to Arizona. How many people go from Washington back to Washington somehow. I don't know the going back, I think it's moving within Washington. So there's a self loop, Florida, people move from Florida and move within Florida or within this particular region. This is a way of representing both the networks being the selected regions, and also encoding information about that particular region and how all these things are connected. It's a fascinating video. I really like it. It also shows brushing and linking, in case you're wondering. Alright. The adjacency matrix. I find them hard to read, but I also am not doing this professionally all day, every day. An adjacency matrix allows me to do, if I look at this, there's a lot of lines here. And especially for really, really, really big data sets, it gets overwhelming. I can't spread them out far enough. I'm going to get overlapping. So an adjacency matrix says this. Well, I'm just going to instead of doing the circle and lines, I'm going to use a matrix. I'm going to use a table and say, if A is connected to A, it always is, make it, or I can leave it off, depending if I have self loops. So A is connected to B, so let's do this one. A is connected to B, so I'm going to color in this, and I'm also going to color in this because B is connected to A. If I only have one-way connection, I would only have one of those filled in, not both of them. If I have a weight on this, I could put a number in this table, so it would just be a table of values. I also have A is connected to C. Great. Is A connected to anything else? No. So only the colored in nodes are connected. So A is connected to C, C is connected to A. Notice if I have a not undirected graph, that matrix is actually perfectly symmetrical. Everything on the top looks like the stuff on the bottom. This is equal to this. This is equal to this. D and DA is the same as AD, that sort of thing. So we have this perfect symmetrical matrix. So technically, if you have an undirected graph, you can represent it with just a triangle instead of a full table. But with a full table, you can show directed graphs as well. So one way or both directions. You can put weights in these things, and it allows you to show a fairly dense matrix, especially really dense matrices, just using a table versus having this spread out everywhere. So here's what the pros are. It's really great for, especially for dense graphs. Really sparse graphs, better to use a normal node link diagram. But for dense graphs, it's really useful. It's visually scalable, so as things get bigger, the more items I have, it's still readable, and I can spot clusters fairly okay, or fairly reasonably. We'll hopefully see an example of something with a cluster. The row order does affect what you see though. So if, for example, A is connected to D, E, and F, so A over here is connected to a whole bunch of stuff over here on this side, or maybe D is here, or it's maybe A is connected to this one, and this one over here. It's going to look like there's no connections or there's very little connections. It won't cluster because they're not put the order in which in the matrix actually changes how I perceive things. So the layout, much like the layout of a graph, changes how I see things in the graph, the layout of the matrix itself changes if I spot patterns. And it's fairly abstract. A lot of people have trouble getting their head around it, myself included. Though you can see it, but it doesn't really pop the way that a network diagram is. Not as intuitive. And paths are just nasty. So A goes to B. Okay, then I need to go over here and go B goes to C and D. Oh, and then C goes to, so I'll go to C. C goes to B and D. So C also goes to D. And then is D connected to anything? I go to D. Oh, D's connected to F. So is there a path from A to F? Yes, indirectly. But it's hard to actually reason about this. This thing is, I go A to B, B to C, or actually B to D, D to F, thus A to F. But that required me doing a number of steps versus just following a path. There are ways of doing this. So here is a adjacency matrix. If I take this snippet, that's the equivalent. Here is an adjacency matrix. Notice I have this nice series of connections. Everything's sort of connected to each other. A is this central hub. I'll get this pattern, like a line and a line. I'll get a cross pattern. If I have a click, I'll get, here's a click. Oh, it's listed right there, right? If I have just a triangle, I'll get a little triangle like this, right? It's 3 nodes all connected to one another. If I have, I think this is a complete click right here. That's what a click looks like. The patterns can pop out for you. It's just you need to get used to seeing these sorts of things. So this is what the adjacency matrix looks like for this giant graph. And I colored it, we can color it different ways. So this particular snippet that I want to look at, I color it orange. This little snippet that is this particular graph where A is connected to a whole bunch of things, that is over here, and I color that red. So here is co-occurrence of characters on Les Miserables. Notice we have these clusters where for each of the acts as they go through the play, everyone's interconnected with each other, but not everyone in the entire play / book, depending on how you view it, is connected to everybody else. You get these pockets of people that are interconnected with the matrix. Here is a high-class, so genomic material. We're trying to figure out patterns with genomic data and what we see. So this, genomic information is extremely dense. There's a lot of data. And an adjacency matrix allows you to find patterns or things, genes that are connected to each other, and what kind of things are, if things are the same on the same chromosome, what kind of things go together when it comes to genomic makeup. And then you can take all of this and take it one step further and combine your node link diagram and your adjacency matrix. So what if we had an adjacency matrix for more dense stuff? So for the dense information like CMU, These are all people working at CMU. These are people working at Berkeley. These are people working at Xerox PARC. If you don't know what Xerox PARC is, I'm more than happy to give you long lectures about Xerox PARC. Xerox PARC is a place that invented the mouse and Ethernet, for example. It's a think tank sort of thing in Silicon Valley. It's one of the original things that made it called Silicon Valley. Xerox made this research park because they had money to burn. They didn't know what they were doing with their researchers at all, and so the researchers were creating all sorts of crazy things. Steve Jobs went to Xerox PARC to look at things and just poached half the technology there, paid for it, but still grabbed a whole bunch of the technology there that wasn't going to even be used, and made the Macintosh. So he made the graphic user interface and the mouse. There was also Ethernet and about 4 other things there, but he saw the graphics user interface and the mouse while visiting Xerox PARC, and the rest is history. Here's Ben Schneiderman. Ben Schneiderman is connected with every single person in his lab. This is Schneiderman himself right here. And Catherine Plaisant is right here. Notice there's a lot of connections between the two, but these are all of Ben's students that are not collaborating with each other. They're just collaborating with Ben. Ben Peterson, on the other hand, has the students collaborate with each other. If you look at someone like the researchers, the researchers at Dalhousie, for example, are famous for, it would be a complete graph. It's a click, essentially. Everyone's involved in each other's papers. There's very cross collaborating. But if I have a loose connection, like CMU doesn't directly collaborate with people from PARC or directly collaborate with people from Schneiderman's lab. These are all people from Maryland, so they're all sort of interconnected, and Schneiderman connects with PARC, but there's only a couple connections, and therefore you put the highly dense connections together in an adjacency matrix and use the node link diagram approach for the loose or not so tight connections. So we can do the same thing with MatLink, for example, and we can do arcs if we have an adjacency matrix, and we can show arcs between various groups and various things. We can show paths. We can superimpose paths on top of it. We can show how this person is connected to this person by drawing or lining up things on the graph. And this is one of my personal favorites. If I have a map, what I could do is turn my adjacency matrix on its side and then draw lines for the different regions on the map. As long as I put the adjacency matrix on the side of that map, I can then hook up this point here to this point to, what point is this? SA, right? So I just align this and align this. This would be all the different points that, so this would be, if I want to figure out how people in, I don't know my areas in Australia, NT connect to people right here. So NT is right here, okay, and then I need to and then I figure out this thing here is this right here. All right, and yeah, and it would be right here, and that's my point, right? You get very used to it, and if you watch the video, and it's a good video to watch, you can actually see, you can see flow through things, but also the adjacency matrix shows the connections between different towns, but also allows you to follow through this path by just turning it on its side. It's quite a nice little trick. So, next exercise. This is going to be a relatively short video comparatively. I would like you to stop the video in a second, but I want you to pull up visualcomplexity.com after you watch the other videos as well. I want you to pull up visualcomplexity.com and have a, explore around the different ways that people do graphs. I might actually just open up the Google Drive folder again and have you guys post your favorite out of these things, just the URL to one of your favorite videos, your favorite visualizations in here, because it's just seeing how people explore, how people do different ways of representing visualizations. You can see what the pros and cons to each approach are, and where it's ridiculously bad or where it's awesome. I'm kind of curious what the mannequin doll seems to be used for this, but what are you gonna do? So have a look at this. I'm gonna open up the Drive folder soon so that you can actually post your favorite URL for that, and then we'll move on to trees. And we're back. Okay, that's an interesting 2-second stop. So, next up, wait, there's more trees. This is just another graph, actually, and it has the same pros and cons. There is just one little extra quirk in here. They're a particular kind of graph. They're very specific, and from a mathematics standpoint, it should be called a rooted tree. From a mathematics standpoint, a tree is essentially anything that if I break an edge, let's say right here, I get two graphs. Take any edge, I chop it, I get two graphs. That's what a tree is. It's a acyclic. It doesn't have to be directed even. It is an acyclic graph that is with degree 1. Yeah, it's just acyclic graph actually should cover it. So a rooted tree though, for most people, it's I got something at the top, I got a bunch, and each one is the one level down from this is one level down. So this is level 1, this is level 0, this is level 2. Right? That's what most people in computer science call a tree. So a rooted tree, I have a root node. That is the parent class. That is my C colon folder, that sort of thing. And then from there, I have everything that's below that. So this is the parent class in my hierarchy of objects in object-oriented programming. It could be any number of other things. If I have anything that has a hierarchy, trees are the way to go. They're the sort of our bread and butter for anything with a hierarchy. But suddenly layout matters. Now, it doesn't always matter, but it becomes actually important. I can't just put these things willy-nilly. I want to actually have the rooted tree on the top, the grandchild objects 2 levels down, and down from there. I don't just put them random. I don't suddenly put, like, if I put, I'm going to erase this in a second, but if I put this way the heck up there, you're going to read this tree wrong. It doesn't work the same way. So I'm under a constraint on how I lay this thing out. And so location, how it's encapsulated, that sort of thing, is critically important. I want my siblings next to each other so I see things. I want grouping, and I want the child classes to be below or directly next to the parent classes. So here's a parent-child relationship. I have a parent, this is a child down here, and my siblings are listed horizontally. They have the same parent, and that's so they're put in proximity to one another, but it's not the same as a parent-child relationship. There's no actual direct connection. They're connected through the parent node, and the parent node only. And it can be coming up in weird, wonderful ways. So this is a tree map. A tree map is a tree. It is a space-filling, a sort of maximally space-filling tree, so that I have services, which is the parent class, and everything that's listed under services for different stocks is put inside of this. And within there, I can have discount variety services, and so that's a subclass, or catalog mail order services. I put items within those items, like drugstores are a kind of service, and that's listed under here. The amount of space each of these parts takes up is based off of how much of what percentage of the group it is, and all the child nodes are nested inside of the parent node, and so you give different portions, different sizes based off of weightings. For example, like Amazon is a huge company and it takes up a large amount of space. I can also color individual parts based off of how up or down the sales are. So Amazon's I'm assuming this is maybe the stock market price. Let's say it went down 6.27%. It's bright red. The darker colors not as bad, so negative 1.68. It's almost black, 0.69. Green, Fox goes up 6.113, right? I can color it based off of the amount of change, so I can do a gradient scale. This is red-green, not ideal, but red-green color scale. And on top of that, the amount of sizes, how big that particular company is. But within a particular category, I have subcategories. In those subcategories, I slice it up again in terms of where things are. So things that are nested inside of it are subcategories or sub-objects. So my hierarchy is actually physically laid out, and the size of the individual part is based on the weight or how big this particular company is. That is a tree map. These are fairly common. I will say everyone raves and rants and raves about tree maps, how awesome they are. I still, after all these years, cannot read one worth a damn. And it turns out most people are in the same boat as me. They just didn't want to admit that they can't read them worth a darn. Tree maps are actually remarkably hard to read, despite the fact they're extremely efficient in terms of space. And so there's a cost benefit trade off that you have to make with a tree map. They're not ideal, but they are great in certain circumstances. So, activity number 2. I want you to have a quick look at this. I actually opened this up already, so I'm going to balance this and show you a couple of them. But notice trees can come in all sorts of ways, shapes, and forms, right? They still have they're still like a network diagram. They still have nodes and edges, but we also have to show the hierarchy. We have to show how, what the parent is, what the parent of the parent is, and so we can do that in different ways. One of them is using the usual node link diagram. What parent and what it's connected to is always a child. We can do it in terms of some form-filling layout, like a tree map, or we can do hybrid approaches as well. We also have different dimensionality, so like 3D, 2D, and just any old thing. Or if things are actually aligned. So let me have a keep that quick gander at this. So hopefully we have this. Okay, balloon tree maps. Let's close this off. Here are different tree maps that are two-dimensional, that are hybrid. Here is tree maps that have an implicit nesting thing. So Verneuil tree maps. We have orthogonal tree maps. We have sundown charts. We have space reclaiming tree map, icicle plots. We have golden triangle tree maps. Like, look at this. These are all different ways that I can actually represent hierarchical data. That's how important it is for everyone in computer science that people actually make hundreds of these different things, self-adapting sunburst. And so we'll make this as the second part of the assignment, the Google Drive thing. Find your favorite one of these and maybe take a photo or like take a screen capture of this and throw that on the drive as well. So a URL of your favorite network diagram type, and then either an image or the URL for your favorite one of these. So this would actually be the URL for this particular tree map, or for this particular tree diagram. Okay. I thought I wasn't going to talk for more than 20 minutes. I seem to talk a lot. So with that being said, that's how I wanted to end everything with trees. Let me also come over to trees and networks. Okay, there we go. So I want to make sure I didn't miss anything out. No, that's where I wanted to end it. So I'm going to stop the video now. I want you to post whatever you find on the Google Drive, and then from next time around we have a number of different topics that we have to look at. So, and we can always discuss which topic you want to get to next. So we have maps and storytelling is one of the big ones. We have scientific visualizations and spatial layouts. Dimensionality reduction might be a bit too heavy-handed. I might just leave that off. That's things like multidimensional scaling. It involves math. And how to give a great presentation. And I like making sure people hit that at some point in time. Those are the next number of lectures I wanted to examine. But I really want to make sure I spend some extra time on storytelling and maps, because it seems to be important both to your projects near the end, but also important to what you guys are doing for your degree program. And so I want to put a bit more polish on that, and I'm going to spend maybe a couple lectures on that. Okay, with that being said, thank you for listening, and hopefully you'll hear from me soon. Thanks.